Hey guys, today I will present a solution to Romania Supplementary TST 2004 problem 2. Firstly, we'll have a look at the statement. We are given two positive integers, m and n, such that m is less than n over 2. Now we consider n distinct unit vectors, v1 up to vn, such that for any line L through the origin O, there are at least m of these vectors on either side of L. Now we are asked to prove that the length of the sum of these vectors is at most n minus 2m. To begin, we want to get a nice interpretation for the given condition. Therefore, let us consider some unit vectors. So this is the origin and this is the unit circle on which we want to now consider some unit vectors. And to maximize this sum, they should all go about in the same direction. Here we can see why our condition becomes useful. Because if all of those vectors point in the northern direction, so we also get a sum that goes northwards, then we would be able to introduce the line that goes perpendicular to that direction. So let's take a look at that line L, and we wouldn't get any vectors below it. Now, of course, m is a positive integer. For instance, if we had m equal to 2, this would be a contradiction because we need at least two vectors on either side. So this would be required. And that already tells us that we can't quite get a sum that is equal to n, because we need to have at least two vectors that do not contribute in the direction of the sum, which immediately gives us a bound of n minus m for our desired sum. In this example, we see that we are quite lucky, because those two vectors that do not point northwards actually go to the south, which gives us the stronger bound of around n minus 2m, because here we have n minus m vectors contributing positively to our sum, and then these m equals to 2 vectors contributing negatively, which yields the bound n minus 2n. But we do not have to be so lucky. On the other hand, we could be in some configuration where we have like many going to the northward direction, and again, without loss of generality, the sum should be something like this. And now we introduce our line, but we could be in a case where those vectors that do not go north go east or westwards, so they do not really contribute negatively. And now we have to think about why even in this case we can get a bound of n minus 2m. The idea is that we can take a look at lines that differ a little bit from our east-west line L. For instance, if we rotate it just a little bit, such that this one vector right here that doesn't go in the northern direction is now above that line, then at this point we only have one vector below it, so we know that we must have another one that goes in the direction such that this angle here is less than 180 degrees. We now have a lot of information about how to approach this problem intuitively, and now I want to write all of these things down step by step. Firstly, to write down our idea that it is a good idea to consider a line L that is perpendicular to the sum of our vectors, we introduce a coordinate system. So let's introduce a coordinate system such that O is equal to 0, 0. Without loss of generality, we may now assume that the sum of our vectors goes in the upwards y direction, or in other words, v1 plus up to plus vn is equal to 0, y hat, where y hat is greater than or equal to 0. Taking L to be the x-axis now tells us that there are m of these vectors at least with a negative y value. Moreover, we assume that our vectors v1 up to vm are ordered counterclockwise. Therefore, we find an index I such that all of the vectors vi up to vi plus m minus 1 have negative y value. For that, we write y of vi up to y of vi plus m minus 1 less than 0, where we define for any vector v equals x1, y1 that x of v should be x1 and y of v should be y1. I want to note here that we take our indices modulo n. In other words, we define Vj to be equal to Vj plus n. For the second part, we now want to use this idea of rotating L. And to do that, let us define L of Vj to be equal to Vj minus m and R of Vj to be equal to Vj plus m. This tells us that the counterclockwise angle from L of Vj to Vj is less than 180 degrees. Because otherwise, the line L through the origin and L of Vj minus Vj would be a counterexample, because it would have only the m-1 vectors Vj plus 1 up to Vj plus m-1 on one side of it. And now we can also get a similar result for Vj, which is equal to L of R of Vj, and R of Vj, namely that the counterclockwise angle from this one to R of Vj is also less than 180 degrees. We notice that if we take a look at this vector Vj and this vector R of Vj, that because this angle is less than 180 degrees, the sum of those two vectors has a negative y value. On the other hand, if we take a look at that vector and any other vector which is in that counterclockwise direction close, like for example that one, then their sum has indeed a positive y value. So why is that? The reason is that this vector is on the left and that one on the right. So we're going to divide our circle in 4 sectors, and if we take a look at any such vector right here and any other vector below this line through it and the origin, then their sum is indeed going to have a negative y value. And the fact that this vector is below this line is exactly equivalent to the fact that this angle here is less than 180 degrees. And analogously, if we take a look at any vector in this bottom right sector, then taking a look at L of that vector, which would lie somewhere here, we would again get some kind of sum with a negative y value. This motivates us to split these m vectors into 2 groups. Namely, we know that we can find an index j such that the vectors vi up to vj minus 1 have a non-positive x value, and such that all of the vectors vj up to vi plus m minus 1 have positive x value. We want to formalize this, so let us take a look at I less than or equal to k less than j. In that case, we're going to have x of vk less than or equal to 0. So we also want to consider R of vk, and in particular bound its y value from above. And well, we know that R of vk has a counterclockwise angle less than 180 degrees starting from vk, and in other words it lies below the line through the origin and vk, or which is equal to the line through vk and minus vk. And since it is a unit vector, we know that its y value is less than the maximum of the 2 intersections of this line with the unit vector, so less than the maximum of y of vk and y of minus vk. And now y of minus vk is minus y of vk, and since y of vk is less than 0, this is precisely equal to minus y of vk. In particular, we get that y of vk plus y of r of vk is less than 0, and we can treat the case that vk lies in this sector, namely j less than or equal to k less than I plus m. Analogously, because we can deduce from this that y of vk plus y of L of vk is also less than 0. All these 2m vectors I've talked about right here are pairwise distinct because m is less than n over 2, and therefore if we consider S, which I will write down right here, to be the set of these 2m vectors, then the sum of the vectors in S is going to have a negative y value. This is enough to finish our proof, because we know that the absolute value of our vectors is equal to y hat, or the sum of y values of the vectors, so the sum of I going from 1 to n of y of vi. Now we split this sum into the two cases that vi lies in S or the other case. So this is equal to the case, well, I'm going to write this as I in S, y of vi, plus the sum I not in S, y of vi. We know that this entire sum here, this is less than 0, and each of those summands here is less than or equal to 1, and therefore we can conclude that in total, because here we have n minus 2m summands, all of this is less than n minus 2n as desired, and therefore we are done with our proof. Here I want to note that we could also interpret a vector on the line L being both on its left and right side, and in that case we could actually obtain the exact equality case.